Just going to start recording now. But it is my pleasure to introduce our first speaker, Daniel Yahalomi. He graduated from MIT in 2018, and he worked with Paul Schechter, who's here. And then he worked with Dave Latham, who's also here, for 2 years at the CfA as a postdoc. And now, just in this past fall, he started working at Columbia as a grad student. So let's welcome Daniel, and he's going to tell us about optimizing an observing plan for Roman astrometry of Terra hunting stars to determine the probability of Jupiter given Earth. So take it away, Daniel.
Hi, thanks for having me, and thanks for that kind introduction. So yeah, my name is Daniel Yahalomi. I'm talking today about a project I've been working on as a first-year grad student at Columbia with professors David Spergel and Ruth Angus. And it's a bit of a mouthful, but the title is Optimizing an Observing Plan for Roman Astrometry of Terra hunting stars to determine this P of Jupiter given Earth, which I'll get into a little bit more later. But this project is very much a work in progress, so comments and feedback are definitely welcome. Okay, so first, just to start, I wanted to take a look at the current state of exoplanet discovery. So if you look at this mass and period diagram, mass versus period diagram, a couple of things stand out. First of all, the primary methods that have been used to detect exoplanets today are the radial velocity and the transit method. And if we place Jupiter and Earth on this diagram, we can see that both Earth and Jupiter lie towards the current limits of our detection capabilities. And the primary cause of this absence in data there is our detection capabilities. It's not a bias in planetary demographics, but instead we've just not been able to have the instrumental precision to detect those. Another thing I wanted to point out is both the transit and radial velocity method are more sensitive to longer periods and to larger planets. So this talk will be in part about astrometric observations, and as we can see, astrometry has not played a very large role to date in exoplanet discoveries. You can see the sole point up here. And so as a brief introduction to astrometric observations, the idea here is you have a planet and its star orbiting their center of mass, and astrometric observations are measuring the relative motion of a star relative to bright nearby stars, and by watching that relative motion, you can see the orbital motion due to its orbiting planets and determine the characteristics of those planets. So how can we best use these Roman astrometric observations of Terra hunting stars to determine this quantity P of Jupiter given Earth, where specifically we're going to attribute the P of Jupiter given Earth to be the probability of a Jupiter analog given the detection of an Earth analog. First, I wanted to take a step back and explain why this would be an exciting quantity to determine. So if we look at planetary formation in our own solar system, the gas giant formation and migration, its evolution over time, has played a key role in the characteristics of our solar system. So in the orbits of inner planets and their stability over time. And this work, has been studied over time in models like the NEAS model and later papers by people like Walsh and Batygin and Laughlin. And another interesting aspect of Jupiter for Earth specifically is that Jupiter may play a key role in the habitability of Earth, primarily in two ways. As I mentioned briefly, Jupiter plays a role in stabilizing Earth's orbit, thus also stabilizing the climate. And secondly, it shields Earth from possibly devastating impacts of smaller objects in the solar system. Another interesting aspect of what we can do if we're able to determine this probability of Jupiter given Earth is we can use Bayes' theorem to then determine the probability of an Earth analog given a Jupiter analog. And to do this, we'd have to use planetary demographics, but the probability of a Jupiter around a G or K dwarf has been studied in papers like Cumming, et al. 2008, Meyer et al. 2011, Fernandez et al. 2019, and they've argued that that probability is around 1 in 9. And this quantity, the probability of an Earth, is one of the primary things that the Terra hunting experiment will be able to provide insight to. And then in this survey, we could determine the probability of Jupiter given an Earth. This quantity P of Earth given Jupiter is exciting. First, just because the amplitude of a Jupiter analog is much higher than the amplitude of an Earth analog. So if we're looking here at the radial velocity signal of a Earth and a Jupiter, you can see that the strength of that Jupiter signal is much stronger. And so in turn, if we're able to, through an RV survey, detect a Jupiter, and we know the likelihood that there's an inner Earth, we could then get a sense of detecting what those characteristics of those objects are. Last year, I just wanted to describe some previous related findings that have done similar work with current detection. So Zhu and Wu in 2018 looked at the Kepler data set as well as some follow-up radial velocity observations and determined that the probability of a Jupiter given interior super-Earth was about 30%. And then using the same Bayesian approach and planetary demographics, was able to argue that the probability of a super-Earth given a Jupiter is about 90%. This is actually interesting because obviously in our solar system, we have a Jupiter analog, but we don't have a super-Earth analog. So this might suggest one way in which our solar system could be unique. And the second survey I wanted to describe this project is this paper by Knudsen et al. In 2014, which sought to determine the probability of a Jupiter given the detection of a hot Jupiter, and found that that was about 50%. And so this is interesting just because I think that it shows precedence of similar studies for previous data sets. So how will we aim to do this? The first survey we'll use is the Terra hunting experiment, which will take 10 years of daily radial velocity observations on HARPS-3 of at least 40 bright and nearby G and K dwarfs. So HARPS-3 will be a fiber-fed high-resolution shell spectrograph on the 2.5 meter Newton telescope in the Canaries. It'll be quite similar to the HARPS and HARPS North instruments that have been very successful to date. And this Terra hunting experiment is expected to see first light in 2022, and it will be able to detect Earth twins in the habitable zone, which was argued in this simulations paper by Hall in 2018, where they showed that Terra hunting experiment should be able to detect Earth analogs both in single and in multi-planet systems. And so just as a refresher, in case anyone's unfamiliar with the radial velocity method, with the radial velocity method, you have, again, a planet and its star orbiting their center of mass. But in the radial velocity method, you're looking at the spectra that's emitted from the star and the relative blue shifts as the star moves towards the observer and red shifts as the star moves away from the observer. And by looking at this, relative Doppler shifts over time, you can paint a picture of the radial velocity to and from the observer, and thus the planetary characteristics. The second mission we'll use is the Nancy Grace Roman Space Telescope, which will have a 0.28 square degree field of view, which is 100 times larger than Hubble, while it has a 2.4 meter primary lens, which is the same size as Hubble. And the Roman Space Telescope, which was previously called WFIRST, so the WFIRST Astrometric Working Group in 2019, argued that for bright nearby stars, so stars within about 10 parsecs, because the astrometric signal scales with distance, should be able to detect Earth analogs, should be able to detect more distant planets with periods up to 10 years by combining data from Gaia astrometric observations, and should be able to achieve astrometric precision of up to 1 to 10 micro arc seconds. And now the Roman Space Telescope will launch in early 2026. We'll have 5 years, a 5-year primary mission at infrared wavelengths and no proprietary time. Just one more time to nail home what these astrometric signals look like. Again, we have the same picture of the star and its planet orbiting its center of mass, and we're looking at the relative motion of that star compared to bright neighboring stars. And so what's exciting about combining these two surveys is that radial velocity and astrometric observations are quite complementary. So I want to highlight two of these main ways are complementary. First, radial velocity observations are a one-dimensional function of time. You're only observing the velocity towards and away from the observer. So there's a mass inclination degeneracy unless you can only determine the minimum mass of an orbiting planet. Whereas astrometry is a two-dimensional function of time. You're measuring the position over time. And so you can break the mass inclination degeneracy and determine the actual mass of the planet. And this is, in this way, it's somewhat similar to transit surveys, where if you can detect the transit and a radial velocity, you can break the mass inclination degeneracy. However, in this situation, obviously, you don't require transit in order to do so. And the second way that these two methods are complementary is that radial velocity observations are more sensitive to shorter orbiting planets, so planets closer to the star, as the RV signal scales with period to the -1/3, whereas the astrometric observations are more sensitive to longer orbiting planets, so planets further away from their host star, as the astrometric signal scales with periods to the 2/3. Okay, so now looking at what we will actually do. So our first step will be to create a set of planetary parameters to simulate, and we're going to do so using 3 populations. We're going to simulate a Jupiter-like set of planets, and Earth-like set of planets, and a set of planets with both Jupiters and Earth analogs. And the reason to do this is we want to be able to, we want to ensure that our observing plan will be able to detect both Jupiter analogs and Earth analogs in all of these setups. The second step will be to simulate the radial velocity and astrometric signal, and then the data based on orbital parameters and an observing plan. And lastly, we'll have to optimize this observing plan of the Roman observations to detect both these Jupiter-like and Earth-like planets. So putting this as kind of the full picture of where we'll start to go. And our plan is to use this, use the exoplanet code, which is by Foreman Mackey et al. In 2021. It's in prep. And the exoplanet is a gradient-based descent modeling code, and so it can efficiently model these planetary systems. And I'm happy to talk more about specifics with that and why we chose that modeling code, if anyone's interested in that. So again, just to summarize, we're seeking to determine how can we best use Roman astrometric observations of Terra hunting stars to determine this quantity, the probability of a Jupiter analog given the detection of an Earth analog. And thank you. I'll take any questions, comments, feedback.
Great, thank you. If you have questions, just use the raise hand feature. I'll call on you, and you can unmute yourself and ask your question. And if you don't want to do that, or your mic's not working or something, you can type your question into the chat and I can read it. While we're waiting for people to find their raise hand button, I will ask the first question. So you mentioned that in astrometry, the longer periods are easier to detect, but there must be some limit for the observing baseline. What is the plan for the Roman observing baseline, and how does that impact your detectability of true Jupiter analogs?
Yeah, so it's actually been argued and shown that the astrometric detection scales, you can only really determine the orbit of a planet if you have a baseline of observations that's similar to the period. And so that's why Roman is actually, one of the reasons why Roman astrometry will be crucial, because Gaia observations will have several years of observations. And then by combining in astrometric observations with Roman, on top of that, you can get a baseline out to the 10 or so year period of a Jupiter analog, and thus be able to detect those planetary types.
Oh, that's great. So you'll be able to combine. There'll be no problem combining the Gaia observations and the Roman observations.
Yeah, that's the idea, and I think we're obviously still trying to determine what the best observing plan is, but our first step will be to do something similar to the Gaia observing plan. That's like a log linear observing program, and seeing how we can combine those.
Great. Any other questions for Daniel? Yeah, we have, go ahead, Jennifer Yee.
Sorry, I wasn't quite following what you just said about combining Gaia and Roman. And so but it did raise for me the question of, wait, can you explain why we need Roman astrometry if we have Gaia astrometry already? And how this will add to it?
Sure. Yeah. So the
Thanks.
idea is that for astrometric modeling, you require a baseline of observations that's similar to the period of the orbit. And so with Gaia, if we, Gaia will not necessarily have, 10, 12, 15 years of observations of these stars. And so by combining observations with Roman astrometry, you can increase that baseline and better constrain the orbit that way.
In this case, though, you said that you were looking at 40 nearby bright G and K dwarfs using HARPS-3, but I mean, for Jupiter analogs, then aren't there a lot of the bright G and K dwarfs that already have radial velocities over such a long baseline?
Yeah, so the radial velocity signal, if there's a Jupiter analog that's face on, or relatively face on, you should be able to detect the RV signal, but there's also the mass inclination degeneracy there. So by getting astrometric observations, you can break that. And then, yeah, and then also the astrometric survey will help with better determining the Earth masses of those objects as well.
Okay, thank you.
All right, Dave.
So Daniel, this is an interesting sounding project, but it doesn't sound like a PhD project. So what are you doing putting effort into this as your first year? Is this a research exam kind of project or what?
So the Columbia program has you do kind of contained one-year projects your first 2 years. And so this is a project that was exciting to me because it was an interesting look into something different than obviously what I did for 2 years at the CfA, but also something that I could work on and tie a bow on and then move on to something different.
Okay.
Well, it's great that you can do such an impressive project in your first year at grad school. All right, if there are no other questions, let's thank Daniel again, and we'll go. I'll turn it over to Griffin, who will introduce our second speaker.
Great. Our second speaker is Jared Goldberg. He's currently a PhD candidate and NSF grad fellow in his 5th year at UC Santa Barbara, working with Lars Bildston, the West Coast Lars, trying to better understand red supergiant envelopes and their explosions. He did his undergrad at Claremont McKenna College, where he double majored in physics and philosophy. His undergrad thesis work was investigating the effects of accreting high metallicity material on stellar abundances and mixing regions in main sequence sun-like stars using MESA. And he also spent a summer as an undergrad working on signal processing for future space-based gravitational wave missions at the LIGO group at Caltech, just before the first black hole merger discovery. Just missed it. So today, Jared's going to tell us about simulating red supergiants with MESA and their explosions as Type IIP supernovae, which I'm very excited about. So Jared, go ahead and take it away.
I started talking and then I realized that my mic was muted. So yeah, thank you for that introduction, Griffin. Hi, I'm Jared Goldberg. I'm really excited to talk to all of you today about work I've been doing for the past few years, trying to understand red supergiant stars and their explosions as Type IIP supernovae. So I'm going to talk a little bit. I'm going to do this talk a little bit like Mythbusters in reverse. First, I'm going to talk about explosions, and then I'm going to dive deeper into the things that caused them. So first of all, what is a Type IIP supernova? It's type 2 because there is hydrogen in the spectrum. Type 1s have no hydrogen, type 2 have hydrogen for historical naming convention reasons. There's a P because there's a plateau. So these things are really bright, about 1 billion solar luminosities, 10 to the 42 ergs per second, and they stay bright for something like 100 days before they fall off, and the luminosity tail is powered by the radioactive decay of nickel 56 to cobalt 56 to iron 56, which has a decay time of 113 days or so. And I want to remind everyone that I know I'm talking about supernovae. This is a stars and planets and galaxies and cosmology seminar. Inferences from these events are relevant to all of these things. They can be relevant for galaxies and understanding the kinetic energy and feedback mechanisms. They're relevant for cosmology because actually type 2p supernovae, like type 1a's, but somewhat different, can be used as a standard candle because of a luminosity-velocity relationship. They're relevant for stars because they're the end product of the life cycles of red supergiants. And they can be relevant for planets because they spew all of the heavy elements that create the planets throughout the universe. And a lot of the higher atomic number elements are produced in the depths of these massive stars. So when I say that these are the end points of the life cycles of massive stars, what I mean is that there are type 2 supernovae and type 2p supernovae where we have observed, or observers have observed, progenitors that are red supergiants in nearby galaxies. So their progenitors have luminosities of something like 10 to the 5 solar luminosity, and effective temperatures of about 3,500 Kelvin. And there's a growing sample of observed red supergiants that then disappear, and we see a very bright explosion, or transient, and yeah, that's that happens. And so here's just a schematic diagram of a type 2p supernova. So when a massive star, about 10 to 25 times the mass of the sun, fuses in its core all the way up to iron, eventually it's no longer energetically favorable to fuse heavier and heavier elements. And so the iron core collapses under its own gravity in milliseconds. The explosion takes about half a second. A shock travels through the star in the time span of days. Shock breakout happens over hours. The ejecta expands and the photosphere is set by hydrogen recombination, trapping heat in, and slowly, like a delayed release valve, letting the light out. And eventually everything becomes optically thin in the nebular phase over about a year or so. And this is what produces type 2p light curves that I showed on the first slide. And we want to know, what can we learn about these progenitors and about their explosions from the diversity in type 2p light curves. And luckily, light curve features trace progenitor and explosion properties. Here we have now models using, I'm just showing some, just to get a sense of the scaling, some models that we created using the stellar evolution code MESA. It's a 1D open source stellar evolution code that's quickly becoming the industry standard for stellar evolutionary modeling. And then STELLA, a radiation hydrodynamics code to simulate the light curves and solve the rad hydro problem. And I'm varying explosion energy just to give a sense of how these things work. Higher energy explosions are brighter and the plateaus are shorter. Lower energy explosions are fainter, the plateaus are longer. And when we vary the progenitor radius, so if we hold the ejecta mass and explosion energy constant and vary the progenitor radius of the star, which I'm not going to talk about how we did that in this study, but I'm happy to discuss it further, we see that larger radius progenitors have brighter explosions, and smaller radius progenitors also have fainter explosions. And we can gain a little bit of intuition from this just by thinking about the luminosity as being roughly the energy and radiation over the diffusion time. The energy and radiation goes like the supernova explosion energy of 10 to the 51 ergs. And this is just to build intuition, so I'm not concerned with factors of a few. We love tilde physics in Lars's group, the West Coast Lars. And the diffusion time can be expressed as the number of scatterings times the mean free path over the speed of light, which if you massage it a little bit and take the density to be roughly the mass over the radius cubed, you get that the diffusion time is about kappa times the mass over the radius, over the speed of light. And this is a good rough estimate for the luminosity, again, about 1 billion suns. And when you work it all out, you get that the luminosity goes like the explosion energy, so brighter, higher explosion energy, the radius, bigger radius, brighter explosion, and inversely like the ejecta mass, or the mass of the, the mass of the star, the mass of the ejecta. We're waving our hands on the 1.5. And this is good for building some intuition, but real calculations have been done. Popov in 1993 did the calculation for a 2-zone ionized and neutral hydrogen-rich ejecta, which the delayed release valve that I mentioned for photons. And that was revisited by Dan Kasen and Stan Woosley in 2009, Tug Suckbold in 2016, and others. We ourselves built a sample of a few hundred red supergiant explosion models in MESA and STELLA, and we also fit to that suite some scalings, and we recover and refine the Popov 1993 and Kasen and Woosley scalings. So we find that the luminosity at day 50 goes like the ejecta mass to an inverse power, the explosion energy and red supergiant radius to roughly 3/4-ish powers each. And we find that the plateau duration for nickel-rich events, and again, nickel is an observable, you can measure it directly from the tail of these supernovae. The plateau duration is dependent on the nickel mass and the ejecta mass and the explosion energy. Higher energy explosions are shorter. And interestingly, the plateau duration, as we saw a couple slides back, is not really strongly dependent on the stellar progenitor radius. Now, this gives us 2 equations and 3 unknowns, the ejecta mass, explosion energy, and radius, that we want to infer from light curves. And it would be great if there was a third variable that we could use, a third observable. However, and a lot of people have used the plateau velocity, the velocity at day 50, to try and lift this degeneracy. But as I mentioned earlier, plateau velocity is redundant with luminosity data. That's why Type IIP supernovae can actually be used as a standard candle method. And we've seen standard candle method applied to get distances to galaxies with 2Ps in them. The Mario Hamui found it in 2002. Dan Kasen explained it, I think, pretty well in 2009. So this is known, but for a while, people were still trying to lift the degeneracies with plateau velocities, and I don't think we can. But what can we do? So for a given supernova explosion, we can measure the luminosity at day 50, the plateau duration, and the nickel mass from the light curve tail. And that will, then we can look at the scaling laws, which inverted yield families of ejecta masses and explosion energies as a function of the progenitor radius. So this figure here has are the theoretical predictions for what families of explosions could cause a given light curve for 5 different Type IIP supernova events: 2004A, 04ET, 09IB, 17EAW, 17GMR. And the cloud here are 2,000 some odd MESA models that were run with varying initial mass, not metallicity, but we could vary metallicity, the initial mass, the rotation rates, wind efficiencies, overshooting, and the mixing length, alpha, which I'll talk about more in detail later. And instead of just having a clean, easy ejecta mass radius relation, what we see is that just about anywhere in the parameter space of red supergiants, we could find a star. So the intersection of these lines with the clouds, tells us we can have a dynamic range of a factor of 2 in a lot of these ejecta mass inferences, an order of magnitude in explosion energies. And so, well, where do we go from here? Well, if we have a progenitor radius, say here, then we can infer an explosion energy and an ejecta mass. If we've, if we've seen a progenitor, then we know the answer. But if we haven't, then we can look, a few places along these. So to verify the scalings and also to demonstrate the power of this, I just exploded 3 models from this infinity of family of solutions that we could make the same light curve. And just to check, well, do the light curves agree? The answer is yes, they agree very well. So these are bolometric light curves and velocities adapted from Martinez and Burston. The velocities are from earlier studies, but all 3 light curves for all 3 of these explosion models agree basically identically the same. Now, there is some difference at early times. You see a luminosity excess for all of the models. This is an I'll get to this more in a bit, but it's often attributed to some interaction with the stellar halo or whatever dense circumstellar material is around the star. And also, the velocities might provide some insight at early times, but it's also nearly impossible to measure. And the other thing to notice is that if the luminosity on the plateau agrees, then we get the velocity for free. We really can't be using velocities to lift this degeneracy. But we could use a progenitor radius. Now, observers, we haven't completely solved 2Ps. There are still puzzles out there. The bulk properties are captured by the scalings, but there are still weird events like 2009 IB here, where all of our models, because of the high ratio of nickel energy to shock energy, all our models that we can make of it slope up like this. 2017 GMR looks great, but we recover explosion energies of 2 to 5 FO, which are double what's realized in any 3D supernova simulation. And there's this late time excess that doesn't seem to agree with a simple nickel decay power law for the or exponential decay, I mean, for the light curve tail. And again, there is this early luminosity excess that is often attributed to dense circumstellar material. So observers, you keep looking for 2Ps. There's still a lot to learn. So takeaways. The luminosity and plateau duration roughly scale as power laws that we understand pretty well within 15% for these nickel-rich events. Families of explosions can narrow the allowable parameter space. And so with a sample of Type IIP supernovae, we can start to probe these properties, the ejecta mass, the explosion energy, and the radius. And if you have a direct constraint on the radius from a progenitor preimage, then we can say a lot more concretely. And lifting these degeneracies, well, we want priors from observations, either priors on samples of radii with samples of explosions or individual events. And also if there is, say, an ejecta mass explosion energy relationship that 3D simulations or 1Difications of these 3D simulations could realize, like some of the work that's being done by Sean Couch's group at Michigan State, then we can start to carve deeper and deeper into these parameter spaces and unravel these fascinating events. So shifting gears a little bit, we've talked about the explosions. Now, Mythbusters style, we're going to talk about the stars. I want to dive a little deeper into how we really understand the convective structure that the shock travels through and causes these bright events. And I first want to say that our 3D understanding of red supergiant envelopes is limited. So this is from the Kobold simulations from Freytag's website, work done by him, Giavassa, lots of that group ongoing. And they have put a lot of effort into studying the emergent surface intensity and other surface properties in the low optical depth regimes for red supergiants. And one of the things to notice are these large-scale convective plumes. This simulation was actually designed to match observations of the star Betelgeuse, which has made news lately, so little pop culture connection there. And also it's a star we see in the sky that's a red supergiant that we think will explode within the next 100,000 years. And we can also get insights, even though this doesn't look like a sphere, we can get insights from assuming the stars are spheres, modeling them in 1D, using what I did here as MESA. And one of the first things to notice is that mixing length assumptions will strongly influence the stellar radius. Here I have 4 different mixing length alphas, And we can see that there's a dynamic range of more than a factor of 2 in the progenitor radius, or in the red supergiant radius, if we go from alpha of 1 and alpha of 6, to alpha of 6. Now, these are a little bit strawmen in that there has never been at least as far as I can tell until what I've done here that I'll show in a bit, there hasn't been a calibration of 1D mixing length theory to a 3D simulation in the red supergiant regime. There have been done for sun-like stars, and that gets you roughly alpha of 1, and maybe up to 1.5. And there have been calibrations to observations of red supergiant effective temperatures that get you more like the 2 to 3 range. But there's, we want a first principles calibration, so I'll show that. The pressure scale height is a significant fraction of the stellar radius. So if the blob, the convective bubble, goes, is in size roughly the pressure scale height times the mixing length alpha, then we would not be surprised that these plumes are very large and take up large parts of the star. And the other thing to notice is that these stars are not a simple polytrope. You can't just assume that the pressure goes like the density to some power, because the radiation to gas pressure ratio is significant throughout the star. So we really need both radiation and gas in order to understand the convection in these interiors. Now, one more thing. The first 20 days of the supernova, the first 20 to 30 days where we saw that early luminosity excess, is really just sensitive to the outermost 0.01 solar masses of the red supergiant. So here I'm showing how much stuff is outside this photosphere for 3 different explosions of models trying to match supernova 2017 EAW. And in the first day, we're looking at the outermost the outermost 0.1% of the star. In the first 30 days, we're looking out, seeing only emission from roughly the outermost 0.1 to 0.01 solar masses. But by day 50, our scalings are still safe because we are seeing now a solar mass in and a few hundred solar radii in. So we can still be fairly confident in the inferences I talked about before. And by day 50, yeah. So what did we do to better understand this convection? Well, we ran 3D Athena++ simulations. I'm going to talk about one of them here because the others are still reaching a steady state, using Yanfei Jiang's radiation hydro module. And he's been running these and very, very actively collaborating in this work, motivated by the 1D models. And we see, first of all, that there's a flat entropy profile, which entails fairly efficient convection in the in the interior. And then this decline shows that the convection is becoming inefficient either by radiative leakage, when a convective bubble is able to get out a little bit, because it's moving for so long, is able to release some of its internal energy in radiative diffusion, or by superadiabaticity, where a bubble, or a convective bubble that's rising actually has to accelerate in order to carry out all of the flux, and so the entropy profile therefore declines. And also there's this high entropy outer convective region where the convection doesn't really look anything like mixing length theory. And we're still working to understand this. But it should be noted that this outer mass coordinate of 0.01 solar masses actually lies in this outer convective region. So it's no surprise that the red supergiant hydrostatic models don't match observations when we look at early time light curves. So we also see, like the Kobold simulations, these large-scale convective plumes. So here's a time lapse at a fixed radius of 650 solar radii, and over time, over a few hundred days, the plumes start to decohere. And I started this little image already when we've reached more or less a steady state, so no need to worry about that. The color bar here is the cold red dense stuff is moving inward. The hot blue stuff is moving outward. So these are you can see the bubbles rising and then the dense parts falling in. On the right, we have a radial lapse. So now we freeze a point in time, and we can see that the plumes, and those plumes last for about 100 days. We also, if we freeze in time and then move out in radius, we see the plumes are coherent along most of the stellar interior for a few hundred solar radii. So very, large scale convection. Now, we can check these velocities that we're getting against mixing length theory, and ballpark, they agree very well. The velocity predictions here now, the black line on this figure is the convective velocity as gotten from the Athena simulations. The gray shaded regions are where 68 and 95% of the mass is, how fast it's moving. The convective velocity is a function of the RMS velocity in the 3D simulations. And then comparing it to what mixing length theory would predict for this expression from mixing length theory. And because of this large scattering coherent plumes, it's really impossible to use this as the calibration of the mixing length. All of the stuff is moving throughout. And, at a pretty big spread in radial velocity, or in convective velocity. But what we can do is we can compare the 1D time averaged time averaged 3D profile, so they become 1D. Is time average and spherically average profiles to mixing length theory, assuming a radiation and gas equation of state and different alphas. And when we do this, just pay attention to the black line for now. The pressure term here in our gradient includes turbulent pressure, which is not included in 1D models, but it should be included in understanding the 3D models. It follows very nicely alpha of 3 and then starts to jump up a little bit to alpha of 2. And so we can use this now. We get alpha, I say 2 to 4 here. I think 2 to 3 is both more accurate, and I like it because it agrees with saying that agrees with 3D simulate or with observations of red supergiant radii. But so this here is we're seeing higher alphas in the 3D simulations in this regime than we would be seeing in 3D simulations of say the sun, where the convective bubbles are much tinier. I don't know if some of you may remember the Daniel K. Inouye space or telescope that it was looking at the sun, and that picture with convective bubbles the size of Texas on the surface of the sun, which is much larger than Texas. So that's where we're at. There's a lot more to come on this. This is work we're actively doing, trying to understand these 3D simulations, both in the deep interior and in the outer convective region. So takeaways, there's this flat entropy profile with this hot outer region, the large scale coherent plumes traveling through the stellar envelope, a physically motivated now calibration of the mixing length, which is 3 in the deep interior and a little bit less than that, a little bit more than that as you go out. And there's more to come. Or a little bit, less. 2 to, goes from 3 to 2, so. And with that, I want to thank you all, and I yield for questions.
Thanks a lot, Jared. That's super interesting. Let's give him a round of applause in the reactions menu. And we have time for some questions. I'll start with one question myself. I obviously have to ask you a question about the supernova.
Yeah, of course.
So there was a point that you mentioned, but then kind of glossed over a little bit, I would say, which is that it's been shown over and over again that red supergiants have material around them, and then that messes up the supernova light curves compared to your scaling relationships. So my super open-ended question is just what should we do about that?
Well, so first of all, I don't think so. As you say, it's been shown over and over again that early time light curves disagree with early time observations of the luminosity. And this messes up nothing in terms of the scalings that I've talked about, because this, this at day 50, when we're looking, we are seeing a solar mass into the star. The emission is coming, the photosphere has moved deep enough into the star that really we can be confident that we're probing the actual stellar interior by day 50. Now that's not true for superluminous supernovae and other things, but I'm talking about 2Ps here. And the statement really is that, at least I think, is that we really don't understand the outermost 0.1 to 0.01 solar masses of material. Now, I think it's still a bit of an open question as to how much of it is stuff around red supergiants, and we have seen observations of the stuff around red supergiants, versus just these large-scale bubbles and some of the intrinsic 3D structure. And so we're working on that as well, trying to connect to these things.
Yeah, okay, that's actually a great answer. I still worry about that we don't understand the very initial part, because that's what we supernova people spend a lot of our time thinking about. But
yeah, I mean, I agree with you.
Yeah,
absolutely.
Just giving you a hard time.
No, it's
okay.
yeah.
It looks like we have a question in the chat from Andrea Dupree. Do you predict the temperature enhancements of the large convective cells at the surface? And what are they?
So we haven't really gone into, we haven't really studied that in detail. I think I wouldn't be surprised if there was, well, so here I have now the gas temperature on the second panel. And the colors in this plot just represent the scatter. The colors corresponds to just what is the probability, if I'm sitting at a given radius, that I'm going to find a fluid element at this temperature. And so yes, there's both temperature enhancement and also some of the cold stuff. So I guess, yeah, I don't have a lot more to say about the temperature of surface cells beyond there is scatter. Some of the stuff is smashing into itself. The pressure scale height is much larger because we have this more entropic convective region, where instead of being like normal convection, actually radiation is accelerating denser blobs outward, and it looks instead of having the less dense bubbles rising, we have dense blobs being pushed out by radiation. So and that's in the very outer region. But it's a good question, and I'm looking forward to having better answers for you in a month or so.
Okay, Flor, go ahead.
Hey, thanks, Jerry. It's a great talk. I was just wondering, since you're using mostly Stella, I was wondering like how this, for instance, compares with maybe other work that has been done with like SNEC or so, or like has that been done?
Mm-hmm. Yeah, so we compared Stella to SNEC a lot. So the scalings we compared actually against both models with CMF-Gen. These scalings we compared with models of from CMF-Gen and models from Dan Kasen's Sedona, and both of those we found pretty decent agreement. The comparison there is in my 2019 paper with Lars and Bill Paxton. We also compared with SNEC. It's harder, SNEC, because it's gray. One of the advantages of Stella is that it's frequency-dependent radiative transport, and that's better for bolometric luminosities, particularly at later times. So it's kind of hard to do an apples-to-apples comparison of Stella with SNEC. I did a lot of that starting up, and the light curves agree pretty well at early times, and then the SNEC light curves start to decline. Another thing that we have in our MESA explosions is an implementation of Paul Duffel's RTI mixing scheme. And so what that manages to do is that sets the mixing. We don't, we can add a couple of extra boxcars, just to smooth it or something, but, and that also mixes both the density profile and the composition. So SNEC light curves oftentimes you might see, and light curves in a lot of other models you might see at the towards the end, you might see like a little ski ramp or something because there's a dense block that's still in there that hasn't been wiped out by the Rayleigh-Taylor instability. And we don't see that in our models specifically because we have this implementation.
Well, thanks so much.
Yeah, good question. Thank you.
Okay, do we have any last questions for Jared? All right, let's give him another round of applause. And I just wanted to remind everybody that we have schedules for both the speakers today. You can sign up for meetings. There's still some space left.
I'm on the West Coast, so I can meet later as well.
Yeah. And thanks everybody for coming to our last seminar of the semester. Thank you for sticking with us online throughout the last year. And hopefully we'll see you again in person, fingers crossed, in the fall. And enjoy the rest of the week.
So Daniel,